Hi guys, after this proof of concepts for realizing functions that can call functions, we can go the whole 9 yards implementing functions that receive parameters, return values, and use local variables. And for all of that, we will use the stack. Let's review the pattern for implementing functions and using functions used in this last video. We had this caller, which was calling a function, and the caller first had to prepare the stack to do this first half of this push of the return address. Then the caller was actually calling this function, and after the return, it had to finish this pop instruction for getting the address from the stack. And for the callee, that means the implementation of this function, we basically had this pattern that first we had to complete this operation for pushing the return address. Then we could do our actual job, the function body. And then in the end, we were fetching the return address. We did the first half of this pop instruction. And now this pattern will be extended. We will first look at the caller. What has the caller to do if the caller is passing parameters and after the return receives some return value. And then at the callee, what the callee in addition should do if the callee, for example, uses local variables. We will first focus on the caller side. What needs to be done to call a function that expects a certain number of parameters and returns a value. And before we actually do that, consider this more general case, let's review in a bit more detail what needed to be done in this last proof of concept example where functions could call other functions in order to call such a function. Before the call, we needed to prepare the stack because the callee needed to store in its first instruction the return address on the stack. And after this first instruction, the callee actually could execute its function body, call other functions, print something. And that means in the function body, the stack pointer might have been changed by the callee. But we expect that after the call, the value of the stack pointer will be the same as right before the call, so that we can simply restore the stack by incrementing the stack pointer by the same amount that we previously subtracted from the stack pointer. And then the call of this function is complete. And of course, for a more general case, this might be a bit more complicated, and certainly we have to reserve a bit more before a function call. Let's consider a simple example where a function expects 2 parameters and will return 1 value. And for simplicity, let's assume that all these values have a size of 8 bytes. Then it's easier to deal or to avoid problems with alignment restrictions. Then we certainly need to reserve a bit more space on the stack before the call. Because before the call, we will first store the parameters on the stack. And after the call, we expect that we can fetch from the stack the return value. And then, of course, as before, the callee needs to store the return address on the stack. And you will see that when we deal actually with the callee side, it will be convenient for the callee to have some extra space on the stack for storing a so-called frame pointer. Now, we do not deal here with the callee yet, but there will be a clear convention where on the stack, relative to the stack pointer right before the call, all these things, and in particular the arguments, the parameters, and the return value will be stored. So that after the call, when the stack pointer still has the same value as before, we can fetch, for example, the return value, and then we can complete the function call by incrementing the stack pointer as before by the same amount that we previously decremented the stack pointer. And then the function call is completed. Now I will actually show you in an example how to call a function before I actually show you how to implement the callee. And in this first example, this function will not have any parameters, but it will return a value. Like in the example for the proof of concept, the registers 1, 2, and 3 will have a special meaning in our calling conventions. And now these conventions will be extended, but not for registers with a special meaning, for offsets. Offsets where relative to the stack pointer, things like the return address, the frame pointer, and so on, the return value and arguments will be stored. The offset for the return address is 0, and the offset for this frame pointer will be 8. So it's the offset for the return address plus 8. The offset for the return value, rval, is the offset of the frame pointer plus 8. And the offset for the function parameter 0, the first parameter, will be the offset of rval plus 8. And the offset for the second function parameter, f param 1, is the offset of f param 0 plus 8. And now in the start function, which is special, we first initialize the stack as before. And then we call function main, which returns integer, which will be the exit code. And after the call, we will halt with the return value, which I will somehow store in register form. Okay, let's not forget that when I now implement the function call, I have to decrement the stack pointer first, always by a multiple of 8. So 8 times 3 plus the number of parameters, which is here simply 0. And by that I decrement the stack pointer, and in the end I have to increment it by the same amount. And in between I have to do the function call, and after the function call copy this return value from the stack to register 4. So I first have to load the address of the function main, to this register func address. And of course, in general, you have to load the literal for this label from a pool. Then I call the function. And after the call, I fetch the result, the return value from the stack into register 4. And then we can comment this here, halt with return value of function main. And here for testing, we already can just use here a return instruction. Of course, this also should work as before, because we're not doing anything. But we already can check whether we have syntax errors. And it actually also should be executable. Of course, now the return value depends on what we have on the stack. On the ULM, it should be 0. Now, before we continue, we also can already fix a few things in the instruction set or extend it. You will see that we will need negative displacements for the fetch and store instructions in general. And we already can do this now. We just have to specify a new instruction format and use that for these instructions. And this format will be as follows. The field y should be signed so that we can have negative displacements. And this will be relevant for all these fetch and store instructions that have this displacement. And this is, for example, here the case. So we change this here to S, also here, and also here. And above I saw that we still have one instruction that is not having a displacement. We also can extend this now. Because you see in general, we now often have this need to have a displacement. And of course, I provide you the instruction set update on the website. And then I already can build the machine. So this is how the stack looks like when we enter this function. And now we have to think about local variables. Because now every callee also can become a caller, we no longer can have agreements like certain registers belong to the callee and other to the caller. We have to use the memory for storing local variables. And for that, we can use the memory on the left-hand side of the stack pointer. But then we have to be careful, because if we call some other function, then we first have to protect our local variables. Otherwise, we would override with a function call the local variables. So we have to decrement the stack pointer by the size of the local variables. And now we have the next problem. The offsets have changed. And even worse, depending on the number of local variables that we have and the size of these local variables. And this is really inconvenient, because then you have to recompute this offsets depending on how many local variables you have. You have to redo this each time you add some local variables. And this is something we want to avoid. We want to reuse this agreed offsets that we already specified for the function call. So it would be nice to have a copy of the original value of the stack pointer. And that's what we will do. We will first make a copy of the stack pointer before we decrement it. And this copy will be stored in the frame pointer, which is just another register. But then, of course, every implementation of a function will do that. So every function will use this frame pointer for storing a copy of the original value of the stack pointer. So before we overwrite this register, we have to save the value that is already in this register. And for that, we will use this reserved space on the stack. And now we have to think about a clear protocol, what actually should be done before we begin with the function body, what should be done at the beginning of the function. And then also, what should we do before we return from the function. Every function will begin with a so-called prologue, and this prologue consists of a few instructions that make sure that in the end, the stack pointer is decremented before the function body begins, so that our local variables are protected from function calls. But before we decrement the stack pointer, we want to have a copy of its value, so that we can access this return value and parameters by the same offsets that we already specified in the calling convention. And we want to have this copy in this frame pointer. So inside of the function body, everything will be relative to this frame pointer. So before we overwrite this frame pointer register, we of course have to make a copy of it. And for that, we will store it on the stack. And before we decrement the stack pointer, we also should already store the return address. Then you also can use the same offset that we already specified. And from this requirements, we basically have some kind of order given to us in what order these instructions should be done. And you will see that except for this decrementation of this stack pointer, this block of code is always the same. Only the decrementation of the stack pointer depends on the number of local variables and the size of these local variables. And after this prologue, the function body begins. And after the function body, before we return, we have a so-called epilogue. And in this epilogue, of course, in the end, we want to make sure that we return to the return address. So we have to fetch the return address from the stack. And before we do that, we first have to restore the value of the stack pointer, so that we again can use the same offsets that we already agreed on. And we also should restore, of course, the value of this frame pointer. And for restoring it, of course, we have to fetch the safe copy from the stack. So also here we have some kind of order given. And here you will see that restoring the stack pointer to its original value can be done easily by just copying the value of the frame pointer back into the stack pointer. So here we actually do not have to increment the stack pointer by hand. And in between, we have this function body, and the return value hopefully will be stored on the stack by some return statement, basically, in this function body. So now we finally can have a real implementation of this function main. And in the first version, of course, it will be simple. It will not have any local variables. We can extend it later. It will just return a value, 42, of course. So I begin here with this prologue. That means I first store the return address on the stack. And in the prologue and epilogue, everything is relative to the stack pointer. And I also use, of course, the offsets defined above. And then I save the frame pointer also on the stack. Then I copy the current value of the stack pointer into this frame pointer register. And then I have to decrement the stack pointer by the size of the local variables. In this case, I actually do not have to do that because I will not have any in this first version, but I still want to keep it as simple to reuse as possible, because basically I will just copy paste this blocks of code later and change certain things. So the 0 here is just the number of local variables times 8. That's by what I have to decrement the stack pointer. So after that we have the function body, and then we have the epilogue. And here I'm basically just reverting things in the right order. So I first restore the stack pointer, then I restore the frame pointer by fetching its original value from the stack. And again, here everything is relative to the stack pointer. Now we have the old value of the frame pointer, and then I finally fetch the return address. Okay, and now I can actually begin with the body of the function. And in the function body, everything is relative to the frame pointer. And that's kind of easy to remember. That's why you develop these patterns. So I just copy this literal 42 first in some register, and I can use here any register except of register 1, 2, 3. And then I store it on the stack. And that means I store register 4 relative to the frame pointer, and the displacement is rval. And that's it. So that means now we already can test it. It should have exit code 42, of course. And now, of course, we can again extend this program so that it's calling another function and that it's also having a local variable. And let's do this in a simple case, also to show you that you basically can reuse most things. So this will, of course, be function foo. And initially, it also will not have any parameters, also not local variables, but it also returns 42. And now we will do the following. We will call this function, and we will just return the value of this function plus 1. So actually, this function foo, of course, should return then 41. Okay, that means now we need a function call, and here just to show you that this is something that actually a compiler should do. Let's copy paste this code here. And maybe I should do the convention that this statement like comments here indicate that I'm describing what this would be in C, and if I use this slash comments, then it's describing the structure. So here I now want to call this function foo instead of function main. And because we have the same signature, we have one return value and no parameters, everything will be the same. Then we get this return value, and here inside of a function call, like in the prolog and epilog, everything is relative to the stack pointer. We will store the return value in register 4, and after this function call we want to use this. We want to add 1, so add q1. We just increment it, and now we want to return what we have in register 4. That means we now store it on the stack. And now we are in the normal function body code. So now everything is again relative to the frame pointer. So we store it at rval relative to the frame pointer. Okay, again 42. And just to show you that this is really the result of this 41 and not some previous code. Let's change this to this unusual value 44. And now, of course, we can also define function foo as a function that receives some parameter or 2. Let's say the first is A and the second B. And of course, all values have the size of 8 bytes to keep it simple. Then we do not have to change anything here in this code. The caller needs to change something. The caller needs to provide us the parameters. And here in the function body, I just want to return A plus B. And then I have to fetch the first parameter. So I could use, of course, here fparam 0. This is relative to the frame pointer because we're in the function body. I could fetch this into register 4. But of course, here it might be convenient to use EQ directives. And also for the second parameter, and then it's a bit more readable, and this is always a good thing in assembly programming, to have it as convenient as possible. So this goes to register 4, and then here I'm adding this two registers. And I store the result in register 4, then I do not have to change here anything else. Okay, and now here we have to change, of course, the call, because we're now calling foo, and let's say we want to call it with 12 and 13. That means now I have to change here this values for specifying how many parameters this function expects, and then I have to store this value 12 on the stack and 13. So that means I first have to load a literal into a register and then store this register. And I can use here register 4. It's okay. So this is the first parameter, or prime 0. Here everything is relative to the stack pointer because we're in the caller side. And then I just copy paste this here. Oops. fparam. So if you have this undefined symbols, just usually use tail or cat, and then you see param 0, param 1 is undefined. Okay. And now we kind of reached the point where we better should document what our program is doing. That, for example, function main returns the result of function foo plus 1. And I will do the following. I will use here in this comments actual C statements. For example, here n equals the result of foo with parameters 12 and 13. And this will be stored in a local variable n. And then later I will write a statement like return n plus 1. And then you will also see that certain patterns need to be applied to translate simple C statements into assembly code. And then you basically already understand how a compiler translates C code into assembly. So for these local variables, I also use EQ directives. The offset for the first local variable will be -8. But actually, we also could use here some general EQ directive. Local 0 could be specified up here. As -8. And then also if we would have more local variables, local 1 would be then local 0 -8 and so on. Okay, and now let's remove here some empty lines. We also could use here, of course, comments. So this here is f param 0 equals 12 and param 1 equals 13. And here we would actually do not need to comment because the comment is already here. We first fetch from the stack the return value into register 4 and from there into our local variable. And the local variables are relative to the frame pointer. And that means after this block of code, we are done with this statement in C. And then you also see writing this innocent line in C causes this assembly output. And now we have this return statement. And the return statement always means that we, after the statement, will jump to the epilogue. That means for the epilogue, we will also always need a label. And here we also need some naming conventions. And this is dot name of the function dot, for example, red. And here we do not exploit the fact that in register 4 we already have this value. We follow the strict rule. If I want to have the value of a local variable or a global variable, I first fetch it from memory. So because we know it's a local variable, we can use this displacement for local variables. And relative to the frame pointer, then we fetch it into register 4. Then we add 1 to this register. Then we store the result of this expression on the stack, and then we jump to the return label. And of course, here in this case, this jump is not necessary, but this is the strict rule for a return statement. First, evaluate the expression, then store the result of the expression on the stack frame, and then jump to the return label. And you do not think about optimizations here. Oh, here it's not necessary or not. You just follow rule by rule. And that means I can provide you for certain things, for assignment expressions first, for return statements like here, for if statements and loops, clear patterns, and you just follow them and you always get a working program because you work like a compiler without optimization turned on. Okay, and that's it. And now it's much clearer what this program is actually doing. As a smart student pointed out, this program still has a bug, and by coincidence, this didn't show up in this exit code, which is actually what I expected, 26. What I should have done is change this here to 1 because I now have a local variable n. And let's first create a case where we actually see the problem in the exit code returned here. I will simply call foo another time after I stored the return value in this local variable n. In this second call, I will not use the return value. I just call this function. And I call foo with 1 and 2. And that means I change this here to 1 and this here to 2. And after the function returns, I will not store the return value in this local variable n. So I just delete these 2 lines. And then we see the following. Now the exit code is 3, which is the result from this second call. Now let's change this subqueue here to be correct so that we actually protect our local variable from this second function call. And then you see this problem is now fixed. So the next thing certainly should be that we modify our functions for input and output so that we can use it with this calling conventions so that we better see what these programs are doing and that we not again have to fall back to look at exit codes. And then of course we also should consider the special case that some functions do not have a return value, procedures or void functions in C. And then we should somehow establish this simple patterns how to translate some C code into assembly. And with that, we will be able to write cooler programs, like for example, computing the factorial recursively, or the greatest common divisor, or quicksort, things like that.